Hey everyone and welcome to PrepFusion. I'm Anish and today we'll be starting the new chapter of control system, that is time domain analysis. So I hope you like the state space analysis part. Okay, I put a lot of effort in that. Okay, and I hope this summary part, right, the last lecture you have watched that, because if you would have watched that, then like all of the concepts will come into like in your mind while watching that lecture, right? And also when you're watching a lecture, right, maybe I would have said this earlier also, that sit down with a rough notebook and all and try to write your rough notes also, right? So you have to keep on writing also, else what will happen is that you will just watch me like solve questions and nothing will get into your head. Okay, so now let's start our time domain analysis. So what is basically time domain analysis? Right, in time domain analysis basically we'll use the transfer function method to analyze our whole system, right? About the stability, about the frequency response, okay, and the transient response, all those things. Okay, we will use transfer function method after this. Before this, what we're doing basically, we are using state space method, right, matrix method, all those things. So yeah, in this chapter we will use the transfer function method. So first this will be the lecture 1. So the lecture 1, right, lecture 1, what we will do, we'll get a brief overview of time domain analysis, and what will come after this, what chapters will come after this, I will give you a brief overview. Then we'll do the step response of first order system. Okay, and few parameters of first order system that will solve, right? After that we'll solve for other inputs as well. Sorry, I should write here is step and impulse response. Okay, so I will make a correction. It is first I will do impulse response, then I will do step response. So first let us know few theoretical points. Okay, not that important, but you have to keep this in your mind to understand the subject wholly, right? So what does this tell us? The time response of a control system means how the response behaves in accordance with time when specified input test signal is applied to a system. Very simple, right? I apply some test signal. For example, let's say I apply a unit step in the input, in the reference, right here. Now I will analyze my output in time domain, and that is basically the time response. Okay, simple, like the name suggests itself, right? So what is this point telling us? The time response of a control system is a combination of both transient and steady state response. I hope Himanshu has already taught you a bit of transient and steady state, right? So obviously it will be a combination of both, right? Initially there will be some transient, it will go from one steady state to another steady state. Why? Initially there was no input, so it was in steady state, right? No, nothing was changing. Now suddenly I applied input, then it will take time for it to go to reach another steady state. So like this it will go, then it will reach steady state, then it will remain there, right? Because my input has also reached steady state, that's why. Okay, now some few of the inputs may happen, they don't reach steady state, basically they are unbounded. Okay, for that we will see what happens. So like this point I hope you understand, it is a combination of transient and steady state. Okay, I will also show in graph there also, you will understand. Now what is the next point? Transient part of the time response reveals the nature of the response. Okay, that is whether it is oscillatory or it reveals with the nature of damping. Okay, and also gives an indication about the speed. So if you don't understand this, no need to worry. Okay, because once I will solve few questions, and there, like once I will give you the proofs, right, mathematical proofs, there we will understand. Okay, speed I hope you understand, right? There previous time we understand time constant tells us about the speed of the system, like dynamic response, all those things we understood, right? So yeah, I hope speed you understand, but if you don't understand the nature of damping and oscillatory, then we'll slowly go into the next few lectures. There I will explain you bit by bit what do this mean. Okay, I just wrote it down here to keep everything in one place. Okay, now what is the fourth point telling? The steady state part of the time response reveals the accuracy or the steady state error of a control system. So what does this mean? Okay, steady state error is a very big topic, we will also do that, but for now just simply that the steady state part, what does it tell? So I have given it some input, let's say unit step, right? Unit step I have given it. Now my output is something like exponential. Okay, and it reaches steady state after 4 time constant. So I want to measure the error. Okay, so what do you mean by error? So for example, let's say I will take this example throughout this chapter. Okay, you have AC in your home, right? So you have AC in your home. Now you make like your room temperature is currently, it's very humid, very hot, it's currently let's say 31 degrees, but you want a bit of rest, and you want a bit of like what do you say, cold, right? Coldness. Now you want to get rid of this heat, so you put that AC to 26 degrees, right, in your remote. So what will happen? basically there is a sensor, okay, that will measure the room temperature and also the temperature that you want, desired temperature, right? Now it will measure the difference and it will give to some input to the controller, right? And the controller then what it will do, it will give some do some mathematical calculations and give it to the like actual AC input, where how much amount of cold air it needs to give out, okay, that all calculations will happen in the system, right? So yeah, basically what is error in this case? The error is basically my output and my desired input, okay, sorry, I am totally wrong. My desired output and my actual output that I am getting, right? Desired output minus actual output. So like let's say I want right now 24 degrees centigrade, right? But like it did the calculation, reference minus room temperature, then it gave out some controller, but for some reason there is always some error, right? So what happens, like it reached to 25 degrees centigrade, then my error becomes 1 degree, right? Like I want 24 degrees centigrade and reach to 25 degrees centigrade, my actual output, right? But there is still error of 1 degree centigrade. Now what will happen? Again, it will give the controller signal that still it is 25 degrees centigrade, we have to further cool the room, okay? So it will give it some more cold air. Now what happens, for some reason after giving some more cold air, like it gave out some more cold air, so for some reason what happened, the temperature, right, directly reduced from 25 to 23 degrees centigrade. Obviously it won't go perfectly to 24, right? It will go slightly below 24. Then again, now there is another error, like the controller will say now the room is more cold than it is required, right? Then what it will do, again it will send some signal to don't send any more cold air, stop the cold air, okay, and let the room heat a bit. So again what will happen, again my temperature will increase, right? So let's say it increase to 24.1. it will go on like that, it will oscillate between the steady state, but at some point it will reach the steady state, or it may so happen it doesn't even reach the steady state. Why, you may ask, why it doesn't reach the steady state? So like what happens is, like in real world problems, right, there are many like non-linearities and non-idealities. So there may be some friction, okay, not in AC but in like real world systems, there may be some friction and other non-idealities, due to which my output will have some offset error. You know, right, in op-amp, like if you haven't studied analog, even though if you haven't studied op-amp like analog, you know that there is some offset error, right? So there may be some offset error, there may be some other non-idealities, due to which my system will cause an error. So we'll see that, right, what kind of error we are getting, also all those things. So like this is what this is telling, the steady state part of the time response reveals the accuracy or the steady state error of a control system, okay? So yeah, I hope you understand. Steady state part gives the error, because during the transient, how will I find out the error? Because that is not even reciprocating what I want, right? Transient is fine because initially my room temperature was 30 degrees and I wanted to 24 degrees, so it will go very fast to 25 degrees, then it will slow down, and then finally it will reach 24 degrees, finally the steady state. That I'm interested in, that what is the actual output at steady state I'm getting, and what was the desired output that I wanted to get, right? So that's why I want to that's why we always find error in terms at the steady state only, okay, not initially, okay? So what does this next point tell us? So the next point here is the steady state response depends on the type of the control system. So what do you mean by type? I've already explained you before also, but here I will still write it. What do you mean by type? I hope remember that type, right? Type of the system means, again this is getting disturbed, system, let me just keep this down a bit. Number of poles at origin in the OLTF, right, open loop transformation. So I hope you remember what OLTF was. OLTF was the product of the that G into H, right? That was OLTF, feedback into my open loop gain, G into H's, okay? So yeah, this is basically my this is basically what my type of the system means. So like I have revising the first chapter, you're revising there, I have taught you everything. So there, right? So like we'll prove this mathematically, like why does it depend on the type of the system, the steady state response. We'll do this for now, just in your notes it should look good, that's why, okay? And what is the next point? The transient state nature of response of the system depends on order of the system. So this one was depending on the type, and the transient response, right, will depend on the order. Okay, how will my transient response look from one steady state to another? That will depend on the order. We will also prove it mathematically. Okay, so like now what is order of the system? So order of the system, right, this is the system. Okay, now what will be the order here? Will it be the order of this one or this one? No, like order will be number of poles obtained from the closed loop transformation, right? So, or you can say order is order obtained from closed loop transformation. So or you can say number of poles of CLT, right? Okay, so yeah, this is my basically order of system. So in this case, what is the transformation? We have already derived it, right? Still I will derive it. So transformation, like we already know, is basically C of S upon R of S. Okay, and like what is the ratio? I will write this directly now. This is G of S upon 1 plus G of S into H of S upon. Okay, so this is my transformation. So now, right, what will be my like poles? Poles will be the number of roots of this the roots of this denominator, right? So how do I find roots? I equate this one equals to 0, then I find the roots of this equation. Okay, so roots of this equation gives me the poles, right? Poles. Now, so how to find the roots? So I will equate this with equals to 0, then I will be able to find the roots as a function. Like this is a function of S, so I will find the location of poles, right? So I will equate this equal to 0. So this is some equation, right? So this is some equation, and this equation is very famous one. So this is has also a name. What is the name? The name is characteristics equation. Okay, this equation, right? So this is basically the name. So like what will be the roots? Roots will be poles, and number of poles will be order like order of the system that I explained already. So yeah, now right, now we'll study the transient and steady state response. Like I was talking about, right, transient and steady state response. So we'll see here what is my transient response and what is my steady state response. So Himanshu has already taught this one, but still we'll see. So like this is a basic first order RC, first order RC, right? Why first order? Because we have only one energy storing element. So basic first order circuit only. So if this is a basic first order circuit, what will be my output? This should be in your tongue, right? This should be in your tongue. Okay, you shouldn't even like think about this for a second. Okay, so my output VO, right, T will be something like this, right? Something like this. Now I think Himanshu has already taught this one. So like this what I'm going to teach you, but still, so it's my duty also. So this part, right, this portion, I can see this portion hasn't still, like this is the transient portion, right, because it is going from one steady state to another one. So this is known as the transient state, known as the transient state, and this is known as the steady state, right? Okay, this is known as steady state. So like here, right, here we find the nature of the response. Like how is my response while applying the input, because this doesn't tell me anything. It is just steady state and it remains there. Okay, so that's why this portion tells me nature of the response. If I suddenly apply input, how my system behaves. Okay, so this one tells us nature of response, And what does steady state information give us? It gives us the error, right, that I told. So what is this voltage? This voltage is equals to 1. Okay, 1. That's why I can see it reaches the full 1 volts, right, full 1 volts. But we know, like, at t equals to infinity it reaches 1, but t equals to 4 tau it reaches somewhat less than 1, right? So that is my error. Okay, obviously at t equals to infinity, obviously it will reach 1. Okay, it will reach 1, but like if you find just before that, there will be some error. That is what I am talking about. But still, if this is an ideal system, so there is 0 error, because at t equals to infinity this reaches 1, and this the input is also 1. Okay, so there may be some cases the input is some other value and the output is some other value, but still there will be some error, and that error will be defined somewhat in a different manner. We'll study that. Okay, so don't keep in your mind that if my input is 1, then my error, like output, has to go to steady state 1, then only, like, then the error will be, then I will be able to find the error, right? So output can go to some other value also. Okay, and input can go to some other value also, and then let's say my input is 1 by 2. Okay, not 1 by 2. Let's say my input is 1 and my output is 1 by 2. So you might say the steady state is half. No, it may not happen. It depends on the system. So error is defined from the system, and how we define the system, error, right? That all those things we will understand later on. So I just wanted to warn you a little bit, okay, just before getting to error, right? Because that is a very students get very confused with that. Okay, so we'll do that. So this steady state tells us the nature of the error. So let me write, can I write it here? Nature of error. Okay, so steady state gives us the nature of error. Okay, so yeah, this was the first thing, and this is, like, as we know, like, this is what we are going to do. Basically this is the first order circuit, right? First order circuit. So yeah, now let's understand few different test signals. Basically, right, what we do, we apply different test signals to the system and measure the output and check the response, right, and see how it behaves. So according to the response, we define the we define the system, like how are they related, and like what are the errors there, and basically the characterize the system, right? So we apply different test signals. So first one is step signal. So step signal, what does it mean? So I give a sudden input, right? Sudden input, I give it to you, and then it stops, right? So I give a sudden input and then it stops. So you change your displacement basically. So what happens is, I give you a sudden input, okay, and then you move a bit ahead and then it stop. Okay, then you stop, move 2 meters ahead and then you stop. I give you a force and move 2 meters ahead and then you stop. So this means this is a sudden input. Now what is the ramp signal? So ramp signal, right? Ramp signal basically is a velocity type input, right? Velocity type input. Input. So let's say you are at a lift, right? Let's say you are at a lift and you press, like, you're moving at a lift and it keeps on moving up and up and up. Okay, it doesn't stop. So what does that mean? Its speed is constant, right? Because lift speed, it moves up at a constant speed and it never stops. It never stops. That means it's like a velocity type input, right? So it never stops and it goes up and up. Displacement keeps on changing, like it is a function of x, right? Displacement keeps on changing. But if for the same case, lift, you like it stops at the third floor, then it's like a step input, right? So your displacement moved to a certain constant value. Like, let's say for a step, what does step mean? It was 0, then it become 1. Okay, so basically lift, it gave a certain input and then it went to the first floor and then it stopped. So that is like a step input. And this one is like a velocity type, because it goes up and up and up and never stops, right? So the displacement keeps on increasing. Okay, now what is a parabolic signal? So parabolic signal, right, is like a acceleration type input. What does it mean? Basically the velocity here also keeps on increasing. So it was moving previously at a constant speed, lift, but now it will move faster. Each second it will move faster. Okay, initially it was moving at 1 meters per second, now it is moving at 2 meters per second, now 3, 4, 5. It increases, like the acceleration is very fast. Okay, this is like an acceleration type input, like velocity keeps on changing. Okay, and what is this? This is like sudden shocks, right? These are like sudden shocks. So basically we do our stability analysis, right? Why is this impulse signal certain shock? I give you some certain impulse, right? Very high force for a certain second, and then it went to zero. That is what impulse is, right? I give you some like lift, give you some jerk, okay, sudden jerk, and then it reached to the same place itself. So suddenly it went up, then it reached to the same place itself. So how can I define that? Like, let's say the lift is free falling, right? Free falling, okay. So it will fall down in the land. It will get a sudden shock, right? Sudden shock, and then it will remain there, okay. That is like an impulse, right? It fall down very hard in the land, and then it got a sudden shock, and it remained there, right? So that can also be an example of impulse. So with this impulse, right, so as we know, like impulse response, with the help of impulse response, we can find the transfer function for LTI system. So what we'll do, we'll do the stability analysis. Why? Because finding the transfer function, we found the transfer function, then the poles will tell us about the stability of the system, right? So that's why. So like here also I will explain all about stability, right? So it helps basically in stability analysis. So stability analysis, how? Basically we find the poles, okay, and from there we characterize it. From the poles we can understand the stability, okay. So yeah, now I have got a bit of tables here. So this is basically analysis using the transfer function model. Previously what we were doing using the state space model, right? So now we'll use the transfer function model. So in transfer function model we have response analysis and stability analysis. So response will analyze the like in two forms, time domain and frequency domain, and in stability we'll analyze time domain and frequency domain. So stability is different. We just want to analyze whether for a bounded input our output is also getting bounded or not. That we want to analyze. Now response, what do we mean? Like what is the transient response? What is the dynamic behavior of the system, right? If I suddenly apply some input, how is the system behaving dynamically before reaching the steady state, right? So all those things will be done here, and all those things like after that will be done here, stability analysis. So in time domain, response analysis in time domain, that is what we are basically doing, okay. What we'll do, we'll give few inputs, right? Like step, impulse, all those inputs we'll give, and we'll check the time response, right? Output of the time response. And next is frequency domain analysis. So frequency domain analysis, we want to measure the response for a particular frequency tone, right? So we give some input like sin omega t and all those things, and then we measure the frequency domain analysis, okay. That in this chapter I think we won't do, okay. So then this is the stability analysis, okay. Stability analysis is basically again for two forms, time domain and frequency domain. So time domain, right? Time domain is like how to know if the system is stable or not. In time domain, how we do that? We do that using the Routh-Hurwitz criteria, okay, and the Root-Lucas. Those two topics help us in finding about the stability of the system in time domain. And in frequency domain, which things helps us in finding about the like stability of the system, polar plot, Nyquist plot, then Bode plot, and all those things, right? And from there we find the gain margin, phase margin. So in all those things are frequency domain parameters, right? So can I write it here? Okay, I will try to write it here. Polar, Nyquist, then Bode plot, gain margin, and phase margin, right? Okay, all these things, like I know you don't understand all this, so let me delete this still, but still these are few topics that we chapters will study, right, next. And in time domain, how we'll do that? With RH criteria, and like with Root-Lucas, okay. Like there are two Root-Lucas, we find the stability, or also other parameters also, and RH criteria, okay. So yeah, these two are there. And like in frequency domain, right? In frequency domain, what do you do? Like in frequency domain, we just give some sine input and check the output response. We just simply measure the response, and here also we give some step, impulse input, and we like find the response, right? So now we will do the analysis for a first order system basically. So what do you mean by first order? First order means order means the number of poles, right? So it is first order. That means here our number of poles will be only one. So number of poles of the system will be 1. Okay, so this is basically what do you mean by first order. So this is basically a block diagram representation of a first order system with unity feedback. Okay, this is the most common representation, right? So that's how we represent a first order system. Okay, with unity feedback, negative feedback basically. Now I will write the governing equation for a first order system. So what is the for a first order system, right? So what is the governing equation? Basically we write it somewhat like this. We have a linear differential equation which is tau of let me explain my output as this time y, okay, and my input as r, right? You can explain that, or you can explain input as u, whatever you want to. So I will explain my output. Okay, I will explain my output as c because here I have given the output as c of s. So this will be dc of dt, okay, plus simple ct equals to r of t. So this is my simple differential equation, governing equation of a first order system. Okay, so governing equation of a first order system. So now with the help of this one we'll find our parameters, right? Time domain parameters, and check that basically transient response, dynamic behavior of the system. But do keep in mind that if the system is not stable, then it is not worth it to obviously check the dynamic response, right? Because the system itself is not stable. What do you mean by stability? I will also explain you that, okay, in this example only. But yeah, if my output I am not getting bounded, okay, so what's the even the point of like if I'm giving some bounded input and I'm not getting some bounded output, then what's even point of seeing the dynamic response, right? Because my system is not stable. First I have to rectify that, make the system stable, then I will check for the dynamic parameters. So yeah, dynamic parameters is important to us, but the foremost important thing is system stability. Okay, that is the foremost important thing. So now can we write the transfer function from this one? So from this one also I can derive the transfer function, and from this one also I can derive the transfer function. So what is this tau? I forgot to tell you what is this tau. Tau is time constant of the system, okay, of the system, and it may also be defined as the inverse of the negative inverse of the poles, or simply magnitude of the poles, inverse of the magnitude of the poles. So 1 by poles you can say, okay, but this is valid for, like, time constant is valid only for a stable system. It is defined only for a stable system, right? Time constant. Or when we have a unit step input, then time constant is defined as the time at which it reaches 63.2% of its steady state value. When we will do the time, like the unit step response, there we will understand it. So this is basically a first order system. Now let us find the transfer function. So I can find transfer function from two ways, from here also and from here also. I will find it in both ways, right? So let's from the block diagram, let's find. So from the block diagram it's easy to find, right? We already know, okay, how to find like simple unity feedback system. So transfer function, right? Transfer function is basically g upon 1 plus gh. That is the formula. I hope you remember, right? So 1 by s tau divided by 1 plus 1 by s tau. Okay, this is equals to 1 by s tau plus 1. Okay, this is equals to 1 by s tau plus 1. So where is the pole? Pole is at minus 1 by tau, right? So basically the definition that I was talking about, it is a negative inverse, like time constant is a negative inverse of pole, or vice versa, both of them you can say. But here, like, time constant is positive, right? Time constant is positive, hence pole lie on the left hand side of the s plane, basically the j omega axis, left hand side of j omega axis. So system will be stable. Okay, I will take one example where the pole will lie on the right plane of the s plane, and I will find the response for a bounded input, and we'll see that it is not bounded, right? Yeah, that we'll see. And from this equation, can we find from the governing equation, simply take the Laplace inverse, right? if I take not the Laplace, simply take the Laplace, not the inverse, simply take the Laplace. So if I take the Laplace, okay, this becomes tau s. Now as I am finding transfer function, initial conditions will be what? 0, right? It will be 0. So it is c of s, and there is also a s here, this s plus c of s equals to r of s. Okay, so what does this become? C, what is c of s upon r of s? Equals to simply 1 by 1 plus s tau. Okay, so yeah, we got the same, right? This is the same like differential equation of that this block diagram basically. Okay, so yeah, this is basically how you solve. So like I will write the definition of time constant in like the another one, okay, in here only. Okay, but when we find the unit step response, there we'll see. So another definition of time constant, this is only valid for a first order system and for a unit when the input is given unit step, right? Only valid for that. Okay, so this may be asked in some theoretical point or something. Okay, that's why. So time constant is known as the, I will give you homework in this so you will understand, the time at which the output reaches 63.2% of its steady state value. Steady state means at t equals to infinity, like this one, right? This was the first order circuit, like the first order RC, right? Where did it go? Okay, we didn't yet solve the RC. Okay, sorry. Yeah, this one, yeah. So here, right? So this is the like the time constant is what it reaches to 0.632. Okay, so after that, like that is known as the time constant. This is the first order circuit, right? As this has only one energy storing element. So from this also you can understand what do you mean by time constant, right? So this is the steady state value, like this one. Okay, and this is the value at which it reaches 63.2% of the steady state value. So yeah, from here you can understand. Where was I writing? Yeah, here, right? Steady state value. So okay, so this is basically that. Now like this is valid for only first order systems, LTI and step input. Okay, so just do keep in mind that step input it is valid. So if there is some other input, then the output form will also change, right? So yeah, that is basically the time constant. So now let's find the responses, right? So we'll find the responses of unit impulse. First we will give an impulse, unit impulse, and then we'll check our output. How is my response looking? So I have already taught you in basic chapter, but still I will again explain, like tell you that if I'm giving the input as impulse, then my output is known as the impulse response. Now that if I take the Laplace inverse of that, that will give me the transfer function, right? So that was the beauty of LTI systems, right? So this is, I hope you are revising the previous notes. It is very important to revise the basics, right? Then all this thing will come together, right? This is known as the impulse response. Okay, if some impulse input is given. So now we know the transfer function, right? What is the transfer function? Transfer function is basically 1 by 1 plus s tau. Okay, so it is 1 by 1 plus s tau. Now like where are my poles? Poles are at the left hand side, right? So this also you can correlate with a simple RC filter, right? Simple RC filter, simple low pass RC filter. This is the first order circuit only. The transfer function, what was the transfer function for this one? I hope remember, right? So here, are there any zeros here? Can we find zeros intuitively? So can I break this link? No, I can't break this link, right? This is some constant value, and can I make this short like this? Can this be short? 0. Z2 can it become 0? I hope you remember I taught you in one of the lectures realizing poles and 0 intuitively. So can it be made 0? The impedance, it can, but s equals to infinity, it goes to 0, but that is not a finite 0. So like, do we have any zeros here? So no, we don't have any zeros, right? Now poles, there is only one independent energy storing element, so there will be one poles, right? So it will be simply the inverse of the time constant, negative, that is minus 1 by RC. So the transfer function will look something like this, 1 plus SRC. Okay, so you can relate it with like this, right? So here the pole is at minus 1, like here the pole is at minus 1 over tau. So now I have to find the impulse response. So what is T of S equals to? T of S equals to simply C of S by R of S, right? C of S by R of S, which is equals to 1 by 1 plus S tau. Okay, so what is my R of S? R of S is like simply R of T is unit impulse, but what is my R of S? So R of S, right? R of S is basically, I have to do the Laplace transform of this one. So what is the Laplace transform of an impulse? I hope you have revised. So what is it? It is 1 by S, right? No, right? It is 1. Okay, so R of S is 1, and so if this is 1, simply I will multiply 1 with this one, then I will find the Laplace transform of output. So my C of S equals to 1 by 1 plus S tau, right? So C of S is this one. So now I have to do the Laplace inverse of this one, right? So if I do the Laplace inverse of this one, what do I get? C of t will be simply exponential function, right? So before doing that, I have to convert this into that 1 upon S plus A format or A upon S plus A format, that, right? So I will convert this. I will take, what I will do, I will take the time constant common. So if I take tau common, right, this is S. Okay, I don't have space, just crunch for space. So this is S plus 1 by tau. So this if I take the Laplace inverse of this one, 1 by tau e raised to power minus t upon tau. Basically it was e raised to power minus at, so a in this case is 1 by t, so 1 by tau, so this is minus e raised to power minus t upon tau, like that you can understand it. So yeah, this is my output function. Okay, so like, let me plot the output. Okay, this is my input, so it is an impulse just at t equals 0. So how will my output look? So initially, right, at t equals 0, okay, this is also u of t. Okay, initially I have, like, put t equals 0, I get a value of 1 by tau. So I'm starting with 1 by tau. Okay, then what is happening? I'm decaying down, right, to 0, infinity, it is going to 0. Okay, infinity, it is going to 0. This is 1 by tau. Okay, so this is dying down. Now for some reason, if my impulse response doesn't die out, right, it goes on. Okay, goes on or is constant, then there is an issue, right? Then there is a problem. If this goes to unbounded, right, like this one, sorry, not like that, this one, so that means my system is not stable. Okay, so that is an important thing to look at us now, right? Let's say if my pole was at the right hand side, what will happen then? Exactly that unbounded thing will happen, that was checking, right? System won't be stable. So now if now pole is on the okay. Now if my pole is on the right hand side of the spin, so what will happen? So let me write it, the transfer function. So here I will draw the S plane, sigma plus j omega plane, right? Okay, let's say my pole is at here at some point alpha, right? Alpha is some positive number, so pole is at S equals to A and alpha is greater than 0. Okay, so let me write the transfer function like this one. Okay, A upon S minus A. Now if my transfer function is like this one, now what will my output? Simply I will find the impulse response. So C of S equals to, I will multiply 1 with this one. Okay, so it will be A by s minus 1. Okay, now we'll take the Laplace inverse of this one. So I hope you remember the Laplace inverse of this one was e raised to power et. This one was minus t because this was plus, right? So that's why we got minus here and we'll get plus here. Okay, I taught you in basics. So the Laplace inverse of this one will be a c of t equals to a e raised to power alpha t, right? Okay, so now can you see one thing, that alpha is positive and t is also positive. So what will happen, it will go unbounded. So for bounded input, okay, like for a impulse, basically at t goes to infinity, it is bounded, right? It is 0. Okay, for a bounded input I'm getting some unstable signal, it is going up and up and up. Okay, so that's why it makes the system stable input, unstable system, sorry, it makes the system unstable. So this is c of t, this is my t, right? So I'm starting from somewhere here, right? From some constant value a. Okay, and then what, I'm going unbounded because it is not settling, right? E raised to power alpha t. So I just took a small example, and what I see is I'm getting unbounded output if my pole is at right hand side of the S plane. Okay, so basically this basically means that poles at the right hand side of like not S planes of j omega axis means system will be unstable, right? Okay, so yeah, this was the main like example I was coming at. So in I think the first chapter also I did one example, but there something got messed, I don't know, I don't remember. But here also I again mentioned clearly, right, what happens if my poles are at the right half plane of the j omega axis. Okay, so yeah, this is what happens. Now few points about the impulse response. Basically we found the impulse response like the state for stable system was this, right? I hope it didn't forget, it was this one, right? Okay, this is the time domain expression. So the impulse response of a system describes the transient behavior of the system. You see, right, we are only getting the transient behavior, right? Only transient. Okay, from suddenly it changed, suddenly went up to 1 by tau and then again decayed down. Okay, so this means the impulse response gives us the transient response. Okay, this is not an important point. Okay, just keep this in your mind. Okay, in a stable system the transient must die out so the system can reach to steady state. Yeah, this is important. The this is also another key point, that for a stable system the transient must die out so that the system can reach steady state. System has to reach steady state, right? Impulse response describes the transient state, so transient state must die out, so this must go to 0 or something. Okay, so yeah, this does die out. That, what does that mean? That means the system is stable. Okay, so impulse response also tells us about stability, right? Because basically it gives us a transfer function, and from transfer function we can find the poles, and poles also tell us about the stability. Like poles, as I said, right, poles lie on the left hand side, then it will be stable, and if poles lie on the right hand side, then it will not be stable. Okay, so yeah, that is what basically impulse response is, right? We already did this in the first chapter also, impulse response, and we found the transfer function. Okay, all those things we did, right? So yeah, that was the unit impulse response. One more point we did in the first chapter, I hope you remember. Can you tell me that if I integrate my impulse response, okay, if I integrate my impulse response with respect to dt and time, what response do I get? Is there any relation between integration of impulse response? I hope you remember, it was the step response. Okay, step response. And why does it happen? Because that 1 by s term comes in Laplace, right? Step has Laplace inverse of 1 by s, so 1 by s also means integration in time domain. Okay, so like that also you can understand. Okay, so yeah, this is one point. And another point is, like, our impulse response should be absolutely integrable for our system to be stable. This is like a signal sense system thing, but still I will write here. Okay, I should write these points here only. Impulse response should be absolutely to be stable, right? So yeah, this is also another point. What does this mean mathematically? So this was the second point. So the first point was basically what does absolutely integrable mean? Absolutely means I will take the magnitude of the impulse response and sum it up throughout the whole t greater than 0 axis, and that should be less than infinity. It should come out to be something finite, then system will be stable. If it is finite, the integration of the impulse response, absolute value of the impulse response, then I will say system is finite. Okay, so yeah, this was basically for the impulse response. Now we will do the unit step response. So basically this time my input is unit step and my output will be called the step response, right? So it is called the step response. Okay, and what is this called? This is called as the basically unit step. So what is the Laplace transform of this one? Laplace transform of this one is R of s, which is equals to simply 1 over s. Okay, which is equal to simply 1 over s. So now right, so like what is the transfer function? Transfer function is same only, right? Transfer function doesn't change with respect to input. So it's like t of s will be c of s upon r of s, which is equal to basically g upon 1 plus gs, which is 1 upon s tau, right? Or I can write it like this one, take the time constant common, s plus 1 over tau. Okay, so now right, what is my r of s? R of s is 1 over s, right? This one. So I will replace this one and put it over there. So c of s equals to, like I will multiply 1 over s on the right hand side. So 1 over s into 1 over tau divided by s plus 1 over tau, right? So now what I have to do, I have to do partial fractions. So again I put s equals to 0 for this one. So if I put s equals to 0, this is 1 over tau over 1 over tau, so it is 1. So I will get 1 over s. Now I put s equals to minus 1 over tau. What do we get? This is minus 1 over tau, so tau goes above, I get tau minus tau basically. Okay, and here I have again 1 over tau, so this becomes minus 1, right? Yeah, minus 1 s plus 1 over tau. Okay, so now right, now let us find the inverse of this. So I will do the Laplace inverse of this. What will the Laplace inverse? Laplace inverse of this 1 over s is u of t, basically we know that. Okay, u of t. And what is the Laplace inverse of this one? This one is e raised to power minus t upon tau. Okay, so u of t also is there, so I will take u of t as common. So my c of t, right, c of t will be 1 minus e raised to power minus t upon tau into u of t. So this is my output response basically. This is my output response. Okay, so this will be my response. Now another way we can do method 2. So this was the method 1, the transformation method, right, to find the unit step response. Is there any other method? Just explained, right, in the previous 2 slides, that I can integrate my impulse response to get the step response. Exactly that I will do to my step response. Okay, I will copy this one. Okay, my step response will be simply integration of impulse response. So what is my impulse response? Impulse response is, okay, let me write this in this side, let me write this in this side. Okay, sorry. So what is my what do you say, what is my impulse response? So impulse response was this one, right? 1 over tau e raised to power minus t upon tau. So put my impulse response like this one, 1 over tau. Okay, what I will do is make this t, right, t dash, because I will get confused with this t also. So 1 over tau e raised to power minus t dash upon tau. T dash is just a dummy variable. Okay, I hope you understand the dummy variables. So this is dt dash. Okay, these are dummy variables, so don't worry, this is just a variable. Let's, like, we can name it x, y, z, anything, right? So we just have to integrate this one, then I will replace that dummy variable in terms of t, right? That is the important part. So this becomes like 1 over tau comes at the outside, this is minus tau e raised to power minus t dash upon tau 0 to t. Okay, 0 to t. So now what will this become? This is basically minus e raised to power minus t upon tau 0 to t. Okay, this is t dash, actually t dash, yeah. So I put t dash equals to t, so it, this equation becomes e raised to power minus t upon tau, and again I put t dash equals to 0, so this becomes 1. Okay, 1, yeah, and this is u of t at the outside. So if I take minus inside, so it becomes 1 minus e raised to power minus t upon tau into u of t. So that is what we are getting right here, basically this one, right? Like here also I got 1 minus e raised to power minus t upon tau into u of t, and here also I'm getting the same result. So yeah, you can check from here also. So basically if I give a unit step, then what is the output that I'm getting? The output that I'm getting is something like this, where the simple RC is low pass filter, basically circuit. So again I'm getting 1 over here, and this, right, this time, this is a tau when my output is basically equals to 0.632. okay, so my output is basically equals to 0.632 volts. That is known as the time constant for a first order circuit and for a unit step input, right, for LTI system basically. So yeah, this is the response of the unit step, right? 1 minus e raised to power minus t upon tau, okay, into u of t. And like here you can see at steady state this is reaching 1 volts and this is also reaching 1, right? Okay, I won't write 1 volts here because yeah, this will be wrong because I don't know the units. Okay, this is just a system, I won't write any units here. So yeah, steady state, this is reaching 1 and this is also reaching 1, right? So now we'll swiftly come to the steady state error, right? So what do you mean by steady state error? So first we have to understand for what systems error is defined. Okay, first let me take a open loop system. Open loop system. So if I take open loop system, then I have been given an input to one system. Okay, and I'm getting some output. Okay, but what is the difference in this one? The input and output are not connected in some other way, right? So I'm not giving some feedback in the system. Okay, hence there is no relation between the output and input. No relation, like no feedback mechanism, and hence there is no relation between the output and input directly. Okay, there is some system and it is directly giving me some output. Okay, so tracking error. Okay, now you might say, why, what are you talking about the error? So basically, right, let's say you have turned on your AC. Again the same example, if you have turned on your AC, right, now you want to switch it to 24 degrees and the outside temperature is 30 degrees. But what happens is AC is just giving it same air, right? Cold air. You turn on the AC and it is giving the cold air. No issues with that. Room temperature is decreasing. But after the room temperature reaches 24 degrees, it doesn't stop. It keeps on giving cold air, right? Cold air. Again, the temperature further reduces to 18 degrees. Why? Because the AC doesn't understand, yeah, my room has reached 24 degrees. I don't need to give any more cool air. I have to stop now. I have to stop, right? But that there is no mechanism to tell it. There is no feedback mechanism to sense that, yeah, I have reached 24 degrees. Now I need to stop. I need to stop giving cool air, right? So that is basically open loop system, right? Open loop system will keep on going. So open loop system, there is no concept of error because I am not able to check anything between the input and output. So I want a desired output, right? I turn on the AC and put it to 24 degrees. So I want that 24 degrees in my room. That is my desired output. But the AC, what it is doing is it is on and it is just giving the cold air. So it is going below 24 degrees, going to 18 degrees. So from there, the AC isn't measuring any error, right? So there is no concept of error in open loop system. That's why no concept okay. So this is the first point, that for open loop system our steady state error is not defined. Okay, steady state error is only present for closed loop system. Okay, as there the input and output are related and I can find the relation between input and output. Okay, so that's why. So here I will come to the definition. So the steady state error of a system response is defined as the discrepancy between the output and the reference input when the steady state is reached. Okay, so like what does this say? It tells us the discrepancy, basically the difference between, in simple words, difference between the desired output and the actual output. So there will be some difference, right? Because there are some imperfections, there are some frictions, all those things, impurities and all those things. Due to those things, okay, our system will have some steady state error. Okay, so that's why the actual output and the desired output that I want to get will be always, there will be some error. Okay, so that's why. So like as I told, right, I want 24 degrees of centigrade in my room, but the AC can only reach to 24.1 degrees. There is some steady state error, right? Okay, that is basically a steady state error. So here, right, one more thing, the steady state error of a linear control system depends on the type of the reference signal and the type of the system. So what do we mean by this? So this, right, I will in next few lectures I will teach you the concept of steady state error. There we will see. Okay, don't have to understand right now. Just for a simple unity feedback system, right? Simple unity feedback system, we'll just study for a simple unity feedback because that is what we have been studying up till now. Okay, later on I will teach you the concept of steady state error for a non-unity feedback. That is very different. So for now, steady state error for unity feedback, right? Steady state error for unity feedback. Okay, so what is the steady state error for a unity feedback? So what I will do, I will take one unity feedback system like this one. Okay, I will take this one, and from here I will like explain you what do I mean by unity feedback. So like error, basic like general definition of error is like this. My E of t, what will be E of t? E of t will be my reference input minus the actual output. Okay, now this reference input, right, this is not constant, this changes, right? This changes. So what is this one? We'll see. So like the reference input is basically how much the output is tracking itself. Okay, so I will explain it to you further in the when we will study the steady state error. For now we just simply study that for a unity feedback system. Okay, for a unity feedback system, my E of t, like this is my reference input and this is my C of t. C of t is coming over here. For a simple unity feedback system, it is just tracking the reference signal, right? Directly C of t is coming over here and it is tracking the reference signal. So this point will be my E of t. Okay, so my E of t will be equals to R of t minus C of t. So like this is valid for a unity feedback system. Okay, okay, so yeah, now this is also another name like this point, right? I will explain this in detail also. This name is actuating error signal, right? Actuating error signal. So actuating, we will go into details when we will study about the steady state error, but for now, okay, let me make this small. Okay, this will get confused. So yeah, this is known as actuating error signal, but yeah, we'll not go into details now. We'll go into details later. So let's find the error for this one, right? So error, right? So error is also defined as for the steady state. Okay, I've already drawn it, I forgot, right? So let me delete this one. Error is defined for the steady state. Okay, so that's why you call it steady state error. So steady state error will be basically equals to limit as t tending to infinity E of t, right? We'll put t equals to infinity in this E of t signal, but we can convert this into Laplace also. Okay, Laplace also. So if I convert this into Laplace, so what does we use the Fan-Well theorem? So okay, let me write here the steady state defined as this one, right? Steady error is defined as this one. So this is basically limit. I use the Fan-Well theorem. What does this say? Limit as s equals to 0 as E of s, right? S E of s. So now what is my E of s? E of s is simply now for this to be valid, right? I hope you know that my E of s has to be stable. Okay, the poles have to be stable, else I cannot apply Fan-Well theorem as we learned, right, in the first chapter. So that is one thing you have to keep in mind, right? So poles of this one, poles of E of s should lie, basically system poles should be on the left hand side on LHS. Okay, so this is equals to simply limit as s tends to 0 minus E of s. Okay, so yeah, this is my error signal was this one, right? Like C of t was tracking my reference input. Okay, this was tracking my reference input. Now if you don't understand this, I will also make you understand when we study the steady state error in details, right? Now for now, just if you don't understand, just go like this, that I'm getting some error signal, right, and then I'm pushing it further to change my controller, basically my AC output. Okay, my temperature is 25, but I want 24 degrees. Okay, so 1 degree is error, so it will give it to the AC and AC will further give more cold air. That is basically what is happening. Okay, so now, right, I can just do a bit of customization here. So I can take here the R of s as common. Okay, now this is basically limit s tending to 0 as R of s into 1 minus C of s by R of s. Now is this familiar to you? Is this ratio familiar to you? I think yes, right? This is basically the transformation. So this will be limit s tending to 0 s R of s into 1 minus T of s, right? So yeah, from here also you can understand that basically the error can also be defined like this one, right? It can also be defined like this one. So let's now understand like what is the stage error for this unit step, right? So what I will do, I will do the time domain analysis and this transformation domain analysis also, both of them, right? So this is the input, okay, and this is the transformation. So from the input and transformation I can find the steady state error, okay. So this is the input, that's why I wrote this formula. This is also an important formula, okay. You have to remember this. So I will write here, this is the important formula, okay. You have to remember this. Okay, so like time domain, we will find time domain. So in time domain, what we know is basically c r of infinity. Now steady state error for like unit step response. So let me take another page. Steady state error for step response, right? So what is the steady state error for step response? So basically my ES of like ESS equals to limit, I will find the time domain and the frequency domain also, as t tends to infinity E of t, right? So what is E of t equals to? Limit, now I will not put limit, I will directly put infinity. So this is R of infinity minus C of infinity, right? So okay, I will put limit because I have to put the value of C also here. So this is t, this is t, okay. Limit t tending to infinity, okay. So yeah, this is my basically steady state error. So now, right, now basically what is my R of t? R of t is simply unit step. So R of t is unit step. And what is my C of t? C of t I got like this one, right? 1 minus e raised to minus t upon tau U of t. Here, right? Yeah, this one. This is my C of t, right? Output. So if I replace with t equals to infinity here, what do I get? So I will not replace now. I will just put this in the equation. Limit as t tends to infinity. This is my E steady state. So this is like E of t and this is like U of t only, okay. So one E of t will get cancelled and we will be left with exponential, right? So minus t upon tau into E of t, okay. So now if I put t equals to infinity here, this is like a decaying exponential. So at infinity this will go to 0. So for a unit step response, my error is 0, steady state error is 0, right? For first order system, okay. For the first order system, we'll see what is my steady state error for like higher order systems and all those things, right? So like I think that is it for this lecture. We did the step response. So let me give you a quick recap of what we did, right? So in the first, I told you few key points that what why are we studying this chapter, and why is time response so important, and what is inside time response. Time response is basically a combination of transient and steady state. So here also one thing, the steady state response depends on the type of the system, and the transient response depends on the order of the system, right? Type means the number of poles at origin in the OLTF, right? So in this case, the type we mean the number of poles in the origin at OLTF, okay. So OLTF is this one, right? I hope you remember that we studied in the first chapter. So first chapter are very important, like all the previous chapters are very important, because for the first chapter every concept will be used in all the other chapters, right? It was a very basic foundation. So order, I know it is obtained from the CLTF, and it is the number of poles of the denominator. So if I make denominator equals 0, that equation is known as the characteristics equation. So this one we'll use very highly, okay? So keep this in mind, this is very important equation, right? So this is also 1 plus OLTF, right? 1 plus OLTF, because this is OLTF itself. So from this parameter, from the OLTF, I can find a lot of information. We'll understand in the next few chapters also, okay? So this is a very important equation. So now I told you like basic transient response of a first order circuit, okay? Then I told you few phase signals, okay? All this, then I did the general governing equation of a first order system. Then we like found the response and like the impulse response. Then we found the step response and also the steady state error. I just gave you a brief overview, the steady state error for a unity feedback, okay? For unity feedback, basically it is the ability of tracking the output, right? So how much error is there between the desired output and the actual output that I am getting. So desired output is my, like for a unity feedback, desired output is my reference signal. Whatever reference I am giving, 24 degrees I am giving, I want 24 degrees, okay? That's why if it is 23 degrees, there will be some error signal and it will give it to the gain, right? So some signal will come out, okay? But this is not totally correct. This block diagram is not totally correct, okay? What is the actual meaning of steady state error? When you will study in a topic, right? I will teach you, then they will understand. But for now, you just understand that steady state error is defined like this one. It is R of t minus C of t, okay? For a unity feedback system. So if I find the steady state error, there are two equations. One is the frequency domain. This one is very useful because we don't need to find the output, okay? We can only, we have to only know the input Laplace transform and the transfer function Laplace transform, right? So only transfer function and input, with the help of that I can find the steady state error, okay? Or if you want to go to time domain, you can solve it like this one, okay? I forgot to solve it in the time domain, right? Okay, sorry, in the frequency domain. So in the frequency domain, what happens? So E steady state, I'll copy this formula basically. So what is my R of S in this case? So my R of S, right? R of S is S times 1 over S, like it is unit step, right? So Laplace of this is 1 over S, and this is 1 minus, what is transfer function? It is 1 by S tau plus 1, right? I hope you remember. Now let me put here, like this SS is getting cancelled, S tending to 0, and this 1 minus this one, so I have two brackets over here. This is S tau plus 1 minus 1, S tau plus 1, okay? So what does this become? So basically this is, right, this is S tau, this cancels out, and I have limit S tending to 0, S tau by S tau plus 1. So now if I put S equals to 0, what do I get? I get 0 by 0 plus 1, which is equals to 0. So my steady state output in frequency domain also is 0, okay? So if you don't want to find the time domain expression, sometimes the frequency domain expression helps to find it quickly, okay? So yeah, this was the procedure for finding it in frequency domain. So in the next lecture, we'll do the other responses for like responses for other inputs, that is RAM response, then for parabolic response, okay? All those things we'll do, and also we'll study a few more first order circuits, few different first order circuits, okay? That will do. Thank you for watching.